All right, welcome back to another week of Haskell hacking and messing around. This week, I wanted to just have some fun and make Snake. Snake is a pretty classic computer game, pretty easy to implement. If you don't know what it is, you're going to find out today. So we're going to start a new project, and we're going to build this. We're going to do it. Stack new Snake. What resolver did I get with this one? 1917. Okay. Cool, cool. So let's open up our project. Snack. And package, we're going to use SDL2. Pretty common game library for writing little game things. Hopefully we have that in our stackage. Might be. See, stackage, 1917, I think it was. 1902 SDL. Oh, sorry, we wanted SDL2. Okay, cool. This is going to be a little bit fun. I've never used SDL2 from Haskell. I've almost always used it from C, except for a little while I was doing some game dev stuff in Python. So hopefully it hews pretty close. Gonna be a bit of a brain melter, maybe. Who knows? So let's get started. We're gonna do source. No, it's app main. That's just going to call some func. We're just going to rename this to, I don't know, run. And that's fine. And then we'll go lib. Call run. Maybe some IO action, and this will be like our main entry point. Looks like to get started, we just initialize the different SDL subsystems. So SDL is nice and modular in that if you only need graphics, you can just initialize just the graphics. But if you need audio, data formats, all kinds of other, there's a bunch of different libraries. You can initialize them separately or what have you. We're just going to initialize all because why not? See how far we can get with this. Of course, I got to do, whoa, thanks for the sub. Or the follow there. Raid train, right on. 17. Ooh, cool. Welcome all, welcome friends. We're gonna make a snack. Because this is also kind of a fun thing to do. Once you know how to implement it, do it well. It's fun to try and like speed code it in a language you're very, very familiar with. Probably won't be able to do that today in Haskell because I'm probably just not that good at it yet. But also, it's just an experience thing. Like, I've implemented this game I don't know how many times in my life. But we're going to do it today in Haskell. It's going to be fun. So we're going to need a window and a renderer. We'll use the renderer API. We'll see if we'll get to bitmap graphics, but we'll start with just boxes and stuff because it's easy to prototype. So we're going to need a window after we initialize all the libraries. We're going to need the renderer from the window to get the 2D API. I'll just copy and paste that in there. And then from there, we need an app loop with the renderer that we can pass in. Pull the events, check all the events and stuff like that. All good times. So I guess app loop, that is there. And we just call ourselves again in typical functional programming style. Recursion is looping. Thick. Okay. Let's follow the similar style. Probably need to import SDL2 somewhere at some point. SDL2? SDL like that? I don't know. SDL, all caps. Okay, app loop. Well, the first thing we're going to do is we're just going to have like some kind of state. We're going to have the X and Y of our SNCC, right? And we're going to imagine our board is kind of like a 2D grid. And we're just going to make our SNCC move across the screen and loop across the screen. And basically that's going to be our first goal here. So I'm going to define a data structure here for the game state. And that's going to be our constructor. The game state is going to have X, which is going to be an int. Maybe it should be a double. I don't know. Let's just leave it int. X and Y. That's all the state we need right now. Okay. So for each pump of our event loop, render draw color, render fill, I think is what I want. Yeah, clear the screen. Okay, so the render draw color, probably set it to black. Call clear to clear the screen to black. Present the renderer what you drew, so on and so forth. Okay, so we are going to render draw color. Linear is a nice looking little library. Where's that come from? Okay, linear. Sounds good. Probably want that. So I'm going to make this undefined for now and then get linear going. Near package. Linear. Okay. Pass the renderer and the game state in. Default initial game state. Initial game state will be a game state. We'll just make this very, very clear. Yeah, we'll make x equal to, I don't know, say 4. Doesn't really matter. We'll make y 10. It really depends on how big we want to make our grid for the SNCC game. This shouldn't be called my SDL application. It should be called SNCC. Now we want to know, I want to know, like, can I force the screen window to be a certain size to fit our grid in there? I guess we have to go to sdl.init. Quit is all good. No, it's going to be probably an sdl.video. Window management, yes. So the default initial size is going to be 800 by 600. That's fine. Maybe we make it a little bit bigger. Window initial size. V2. I'll make it 1200 by 800. Aspect ratio. Okay. So, we'll get the renderer in scope and our game state. Let's use record wildcards, because why not? Although, we're at 902? I don't know if, no. I don't know if the record dot stuff is in this one. So we'll just use record wildcards. That's just what I'm thinking about at the moment. Okay, so that means we got an underscore x and underscore y in scope. And we need to render something using those values. Renderer is renderer management. Oh, is it? There it is. SDL.video.renderer. That's what we want. I want draw rect, fill rect. Fill rect. That's the one I want. Fill rect. The rectangle to fill. Why is that a maybe? What happens if you put nothing there? Interesting. Okay. Why did we fail compiling? Oh, probably because I was trying to compile something that I was like half, not quite done. Let's leave that hole there. We'll get our build going. Stack build fast. File watch. There we go. Set variable. I'm just going to make sure that my environment here is all set up properly. Haskell process type. And extend that to stack GHCI. Okay. So I should have my handy dandy type errors now. Okay, and then I give it my initial game state. Here. Okay. Let's see. I couldn't match a type. String with text. Oh boy. The overloaded string is going to save us here. Maybe not, but maybe it will. And there we go. Okay. Good. Just our hole. That's what we want. So, renderer fill rect takes a renderer. Oh, we got to set the color first. Clear the screen. What was it? My fish memory. No good. Renderer, draw color. There we go. And then clear. Clear renderer. Okay, that's cool. And then we got to present renderer. Okay, minimum viable program. Exec snec exe. Let's see if it pops up here. Oh, what do we call it? Package executables. Snec. Oh, I'm just not in the right directory. Darn. Okay, well, we had a window pop up there for a second and disappeared right away. That's because we're not looping, right? So we'll loop renderer. We'll pull in the state. And that should compile and work, no problem. Let's check it out. Okay, cool. Blue window, snec. Let's make that black. Oh, sorry, we're gonna wait for the recompiler. There we go. Okay, black, good. Okay, so we got the X and Y in scope. We cleared the screen. Let's render fill rect. Yeah. Fill rect, renderer. Rect. How do I get a rect? Don't like that. Yeah. Then I just had to put a rect in there. Rectangle. Or a vector of rectangle. Oh, that's rects. Sorry, I just need a rectangle. Is there a helper function for constructing these to make it easier? Do I have to use the constructor? Ugh. Okay. So the v2 is going to be the upper left corner, and the second parameter, the other v2, is going to be the bottom right. So we'll draw the top left corner at our x and y. Not happy with this because all right, let's just get rid of those. Just make it plain x and y then. It's not the problem, probably. I think I maybe need to wrap it in a point. Ugh. Maybe there's a helper function for making points. PFA. V2, V3, V4. Like that. That made it happy, sort of. P v2. Do x plus some offset. So if we want our, say, block size to be like, what are we, 1200 by 800? So we could do 1200. We could have, if there are 12, that'd be 100 across. And that would be not quite even. No. 20. Yeah, and then 800 by 20 would be fine as well. Nice even number 40. So we can do it by 20. So we'll just off at x plus 20. And y plus 20, say. Now it wants a c int. Ugh. Oh, there's got to be an easier way of making rects here. Come on, folks. There's going to be such a common thing to construct. You gotta have helpers for this. Come on, really? It says v2a, v2a. That's it. Rect. I don't like it. No, that doesn't want to be. It just wants a v2 int. Okay. Yeah. How do I make a c int? Ugh, that's gross. Can I just make him c int on the state then? I don't have that in scope. Okay, let's try importing it. Import foreign.c.types. Well, it compiles. Did it work? Oh, we didn't render it. We just have the fill rect call there. But we didn't set the color to anything, so I can't see it. So let's make it blue. Okay, cool. There's our rect. That's great. Let's make it move. So when we call in the loop, before we start rendering stuff, we'll just make Usually I draw the state, or I update the state first, and then I draw the new state, and go to the next one. Here, it seems like it'll be easier to draw the state we get first, and then update. Which seems kind of weird. Right, otherwise we can do it like this. We can be like next x, so x prime equal x plus, I don't know, say 1. All right, and that'll make it go this way, like across the screen. So when we go to the next state, right, we just set x to x prime. And instead of rendering just plain x here, we'll render x prime. This will kind of make it, this will make it like creep across the screen, probably pretty quick. Blah, 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 blah. Keep tabbing past because I'm not paying attention. Here we go. All right, it's kind of looking kind of gross, but it's getting there. Let's see. Why is it doing that? I was kind of expecting it just to be a square to go straight across. Weird. We're also not really... Okay. Let's see. Interest. I don't know what's going on there. That's weird. Okay. So we pass in the next state. So the first frame, we should have x as 4. All right, and then x prime will be 4 plus 1. So the first state, x prime will be 5. All right, the first frame, x prime will be 5. And then this equation here will be 5 plus 20 will be 25. So that should be fine. And then we present the renderer and render that to the screen. And then we recurse. And when we recurse, we're supposed to set the renderer draw color to black, clear the screen. X prime will be 5 plus 1 will be 6. All right, so now this will be 6, this will be 26. And we render. That's weird, man. That's weird. Okay. What is going on with that? We just did X, for example. That would be off a little bit. And, well, okay. Anyways, that's not kind of logic I wanted. I just wanted to get the box moving, but no, I don't actually want to render it at the pixel locations. I want to render it on the grid locations. So we have to multiply this by our square size. All right, so position X is not in pixel space. We have to like multiply this back out to into our grid space. So we'll say it was said it's like 20, right? y prime times 20. And then x prime times 20 plus 20. Our constant factor is our width here. All right, so that should be the bottom right corner of our box. So the same as the top left corner plus 20. And the x prime, y would be the same thing. Y plus 20 times 20 plus 20. Yeah. Pretty straightforward. We don't have y prime in scope. That's right. Sorry. It's not changing y yet. Now it's going even crazier. What's going on with this thing? Rect, rect, rect. Ooh, is it the width and height? Maybe that's what I'm messing up here. That's probably what I'm messing up. Width and height. So if it's just width and height, then it can be a constant. That's probably what it is. Silly me. There we go. That's what we want. Okay. Yes. Okay. So the rectangle's width and height in the top left corner plus the width and the height it calculates the offset and pixel coordinates for you and all that stuff. Good. So now it's like just shooting off and around, but we want it to wrap so that it doesn't just go off to the side of the screen and continue going. All right. So this value here, the next x prime, should be modulo the width of the grid. What's 1200 by 20 is going to be 100 or 60, sorry. Not quite. That shouldn't need the parentheses. I think that should be fine. There we go. Pew, 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 pew. Cool. So that's the x and y position of it. Let's give it a direction. So we have dx. We'll keep them sequence as well, dy. So the dx variable control the direction of the SNCC as it's moving. So instead of modifying it with the constant +1, we'll add the direction x, mod 60. And that way, our initial state, we can say dx equals, say, -1 instead. dy equals 0. Oh, I don't need the brackets around it anymore. That's right. That was fixed, wasn't it? Oh, that's old Haskell, I guess. Okay, and so now it should go the other way. Just fine. Perfect. Okie dokie. We can do the same for, say, the y-axis now. Y plus dy. Mod it by, is it 20? 40, of course. So the height of our grid is what we mod it by. Okay, so if we wanted to say change that, and we'll make x 0 for now, and we can make y 1. And now it should go, once it recompiles. We're not rendering that properly, of course. So let's go with y prime. And we have to update the state so that x or y equals y prime. And we have to wait for it to rebuild there. There we go. And now we go the vertical motion. And that should be the same as well if we go -1. Yep, and it goes up. Okay, cool. And wraps around. Good. Okay. Now that's rendering a little bit too fast. We need to slow it down a little bit. Now this is interesting. How do we make it go a little bit slower in Haskell? So like in a typical game loop, we don't render as fast as we can possibly go. When we have 60 frames, say we want to render at 60 frames a second, right? In 1 second, you can divide up that second into 60 little slices. And then in each slice, you have a certain amount of time to go, right? To do stuff. And if you're trying to render as fast as possible, you're going to update a lot more than 60 times a second. A computer can render, it'll go as fast as it can go if you just give it a plain loop like this. But we want it to like just render, say, the 60 times or the 30 times a second. And in the space between, now we have time to do other stuff, updates, physics, things like that. And how can we do that in Haskell? That's a good question. Does the SDL Haskell library have an example of this that we can borrow and learn from? It doesn't. Well, we can pull the keys so we can at least quit out. Let's do that. And then try and think about this. So it looks like we just bind all the events. That's pretty neat. Pull events. Let's just steal this. And unless, I think we get that from control.monad unless. Cool, clean that up, make it look good. And then, oh, I have to actually be on the application window. There we go. Okay, so that's how we pull events, and we get the Q press out of there. So we should be able to modify the direction now dx based on the Q press. Kind of like this. So event is Q press event. So they're defining a function here. We pattern match else, otherwise Q press is false. Okay. So we could copy this pattern. I don't know if I like it, but button up. With the event payload of the event. Keyboard. Which means we can check a bunch of things. The sim key code W, say. Otherwise, false. Up button pressed. Cool. And so then when we're updating the state, we just need to change what dx prime is, or dy prime. We'll just leave dx prime the same as dx for now. Dy prime, though, we can make so if it's pressed, we should just change dx prime to be 1 if it's not. Or sorry, -1. So if dy prime is greater than, or is not equal to -1, and up button is pressed, then we'll make it -1, else this won't handle the down case, but I'll fix it. I just want to see it this work. Disable else 0. That's not the right symbol for not equals in Haskell. It should be that. Okay. I'm getting just a couple of style warnings, but we'll ignore them for now. Yeah, if we want to see this working, okay, the input on this, because the OS stuff is a little bit weird. Just because like I'm running this through an X server, so super fun times. So let's set our initial state dy to be 0, and we'll just make x 1. So we're going across. If I hold up the oh my gosh. Is the input even going to the window? I can't tell. Well, Q is, so it must have been. No, leave it as www. Okay, let's see if it works. Come on. I know you can do it, Snake Game. It doesn't like it. I don't know why. Okay. No, 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 no. That's really annoying, though. Okay. Let's case match, pattern match. Hmm. Compare. We'll compare dy to 0. Yeah. Where it is less than 0, we gotta do something. It's equal to 0, we gotta do something. When it's greater than 0, we gotta do something. So the case where dy is less than 0, yeah, let's put a guard on it. Sorry, is greater than 0. And up beaten priest. And then we have the otherwise case for that. Like this, maybe? Seems reasonable. So if the up button is pressed, otherwise we'll just leave it as dy, leave it alone. Otherwise we're going to switch it. And so you go the opposite direction. If it's still equal to 0, we're not pressing any button. Well, we have two cases where it's equal to 0. Either we're pressing a button, the up button, or we're not. If it's equal to 0, we press the up button. All right, then we can set it to -1. Otherwise, we'll just leave it. And in the less than case right now, we'll just leave it. We just apparently just remove, we don't need the otherwise case. We just like, we don't need the guard for otherwise there. Otherwise it comes after. Super. Okay, then we got to use those. Now we got to pass them to the new state. That's probably what was not working before. So dx prime. dy is dy prime. Okay. Why does it do that? There we go. Cool. So I pressed Y, it doesn't, but I don't have any of the buttons implemented, so it started moving Y in the right direction. That's nice. So let's implement the rest of those. So actually, when we have that, we have a couple of things that need to happen, actually. Because we can't have dy and dx. We can't have our snake going on an angle. So we can't really set these independently of each other. Yeah, I don't think we can set them independently of each other, right? I want them to be discrete. So if you press whatever the next button you pressed is, when you press it, it changes the direction of the snake. So if you go up, it goes up. And if on this frame you press left, it goes left. It changes the direction of the snake. Which means we need to set these as a pair. And then check the current state of the snake. So let's do that. I'll move dx dy prime. So we'll compare dx to 0 and dy to 0. Pull this over to the left a little bit. These become tuples that we have to match on now. Okay. So we have quite a few cases here. Less than, and less than. Less than, greater than. Greater than, greater than. EQ, EQ. Oh, it's quite a few. Oh my gosh. We're going to get the product of all the combinations. That's all the cases, right? So there's three states for each, and 3 times 3 is 9, so it should be 9. 1, 2, 3, 4, 5, 6, 7, 8. We're missing, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we're missing 1. Greater than, greater than. There we go. Okay. So in the EQ state, we just care what the next button press is. Yep. Little interesting. Yeah. I don't know if I like this. It's too much. This is a lot. But anyways, so the EQ state, up button pressed. Okay. So we have the up button press. If it is pressed, then we know we can increase, we can set dxy to 0 and, or sorry, dy prime to 0 and dx, or sorry, dy prime to -1 and x to 0. X will be 0, and then we have -1. And it's not is button pressed, it's up button pressed. All right, we could have a similar one for down. Sorry, btn. And down, and that would be the opposite. And if we had left button pressed, this would be 0 and -1. And if we have the right button pressed, this would be 1 and 0. All right. We have to, we won't have a state except for the initial state, I guess, where dx y and dx0 are equal to 0, but they'll stay 0 otherwise. Did I have parsing error on 56? Oh yeah, well, just have to put a bunch of these, yeah. Okay. And the problem here is I'm not expecting a parse error here. Oh, it's just the indentation is moved over. That's right. Yeah, this is actually moved over to the wrong amount, wrong direction. Pow, 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 pow. Why did I do that the slow way? I could have just done that. I don't know. No, that's not quite the right indentation. Thank you. Should be that. Yeah, there we go. All right. That's better. We don't have those defined yet. I'm gonna just kind of make a slightly better function and kind of compress all this up. I'm just gonna call it event is button pressed. Event is key pressed. Key sim. I'll put key sim as a second argument. Key sim. Take this and replace this key code with, or sorry, it should be called key code, not key sim, I guess. And then I can replace Q pressed with event is key pressed with key code Q. No, it should be the other way around. Key code is the first argument. Point free. Yes, and up button, I should be able to do the same thing. Event is key pressed with key code W. Get rid of those two. And down, left, right. Left and right. Okay. And W down will be A, left will be S, and right will be D. Simple enough. What's the problem here? That's the problem. All right. That should compile, and now, hopefully, well, barring any holes, of course. Just replace those with undefined so we can compile it and test it out. As long as our initial state, our initial move state, dy, d0, dx are both 0. All right, we should start from just standing still, and as soon as I press one of the keys, it'll go in that direction. So I go up, it'll go there, that's fine. We're gonna get an error though. This will eventually hit undefined. But you saw it kind of jump the frame there, so. Oh no, we're actually missing greater than, less than. Okay. Okay, so let's do... Let's do this top case, and we'll go down the list, I guess. If they're both less than 0, that means that we shouldn't be able to have that state, because only one should be less than 0. That would mean, because if it was less than and less than, that would mean you're going on a diagonal, and that should be impossible. Same with this one. This one should also be impossible. That would also be the same. That's right. So we only care about the equal states, where one is equal to 0 and the other one isn't. So less than, equal. Those that don't have any equals in them, so that's fine. That is an equal, that is an equal, that is an equal, that is an equal. And this one will be an error as well. We can just get rid of these. And this one, and just make this a wildcard match for anything else. Okay. Okay, so then we just have the cases we actually care about. So if, let's see, direction X is less than 0, that means we're going to the left. In this case, we care if the up button, any button other than left, is pressed. All right, so if we have up button is pressed, we have down button is pressed. What's the other one? We have right button is pressed. All right, and then we have the case where it's the left button being pressed, in which case we just leave it. All right, we don't touch it. So in the case where up is pressed, then we set x to 0 and -1. If it's down, it's the opposite of that. And if it's right, we set x to 1 and 0. Okay, for this case, I think we're going to have a fairly similar experience. So this is dy is less than 0, so things are going up. In this case, we only care if the down button is pressed or the left and right buttons are pressed. And yeah, then the last case, dx and dy. Yeah, fine. Whatever. Okay, so if the down button's pressed, then we flip ourselves to be greater than 1. Otherwise, we set that to be -1 and 0. And this one to be 1 and 0. Sorry, that should be right. Okay, and we're just going to kind of go through this mechanically. So this one is where we're traveling to the right. Here we only care if the left button is pressed or up and down. Otherwise, we leave it alone. There's a bit of a pattern emerging to this structure, isn't there? All right, greater than. And then we press the left button, we make it less than 0. Otherwise, this is like up and down. Yep. And in this case, we have the, we're going down, so we only care about if the up button is pressed. And finally, the case where we don't do anything. Okay, so then if we press the up button, right, 0, -1. Otherwise, it's, say, left and right. There. That's probably the most amount of work I've put into into the different key presses, and I think, yeah, I'm just led myself down this path here, but I think the pattern is pretty obvious, hopefully. that we might be able to refactor this down. For some reason, though, we might not have it quite right. Oh, there it goes. Okay, left isn't working. Oh, one of my states isn't working. Do. Okay, so one of my cases is wrong. We'll fix that. It's the left button when we are less than going in the direction. I wasn't able to go that way. So let's just make sure. In the case where dx is equal to 0, if down left button is pressed, we go to -1. That's right. Oh, sorry, this is when we're going up, we're traveling upwards. So direction y is less than 0. Yeah, so we should only make it go upwards or left and right. Otherwise we leave it. In the case where we're already going left, we can go up. And we can go down. We can go right. When we're going right, we can go left. Ah, that's what it is. Down is A. No, left is S, D. That's right. Okay. And where we're going up and down, we can go left. We can go right. Ah. Was it working just fine? No, it's not. If I press A, I start going in the down direction, so that's wrong. Ah, because we made A the down button. Oh, that should be S. A. Merp. That's better. There we go. Left, right, up, down, up, down. We can't hold two at the same time or more than one. It's just going to go to the most recent one that it matched. Good. Okay. Whew. That's good there. So the next part, now that we have controls going, we could clean this up, but basically I think the idea here is that you just have a matching function that corresponds to an amount that you can add to the current dx or dy to the button, right? This is fine. It works. Let's just move on. Okay, so timing still is a bit weird. We could just put a sleep in there, like wait so many seconds, or milliseconds or microseconds before looping again. Let's see, Unix. Control.concurrent.thread delay. Yeah. Good. That's probably the one we want. Not the best way to do it if you're writing a real game. By the way, don't do this at home. It'll be fine enough for a prototype game like this, like Snake, where we're just trying to move fast and mess around. So we'll do the thread delay. Yeah. That takes a parameter. I just want to check if it's in like what the int means. Microseconds. Okay. Oh, like 20,000 microseconds. And now if I can actually get it to go, it's a little more reasonable of a speed. As you can see, it's not the greatest because like maybe it's not showing up on stream so well, but it's stuttering a little bit. Just increase that a bit more. Say 100,000. There we go. It's not too bad. Okay, so that's cool. Of course, we need a tail. So let's add more game state. The tail. What should the tail be? Like a list of positions that we had before. We're going to need the tail length, the current. Yeah. Yeah, I might need the tail length, yeah. Right, so when we start moving, we're going to like, if our tail length is 3, then we're going to have our head of the snack, which is going to be the front of the snack, the part that's moving, and there's going to be like, say, if the tail length is 3, then there'll be 3 blocks behind us. We'll have the 3 previous positions we were at. There. If there's 3 previous XYs. Right, those could be like a V2s of Cients. Right. And so our defaults tail length will be 0. Or let's test it out. Let's make it like 2. And tail just be empty initially. So the tail won't start growing until we start moving, is the idea. Let's just bring this over a little bit. There we go. Yeah, so that should be good. So we have some more updating to do here. So let's see. We won't worry about updating the tail length for now. like the number, the length of it, until we start adding fruit, which is kind of part of the game, the mechanics. All right, but we will do the tail part. So what is tail prime going to be? What's the next state of tail for this frame? All right, well, we can compare the length of the tail to our tail length. Okay, and then we have the three cases: less than, equal to, and greater than. If it's greater than, if it's less than, then we want to add the previous position to our current tail. And if it's equal, then we do nothing. And if it's greater than, we should do nothing. And that should be an error. That shouldn't even happen. That would be a programming error if that happens, if that invariant is broken. So if it's equal, we can just return the original tail, the tail we have from the last state. And the only case we really care about is when it's less than. So we have to do something here. How are we going to manage the tail list? It would probably be easy, since it's a list, to just add it to the head. Add the last state's position to the head. So then we just have to render them in a particular order. Oh no, we have something to do in the equal case, actually. Yeah. Yeah, in the equal case, we actually do have something to do. So if it's the less than case, let's put the head, let's just cons the last position on. So X and Y onto tail. Okay, so in the equal case, we got to kick one element out, the oldest element, so to speak, and put the next element on. Right? So what we're going to do then, this only works if tail length is greater than 0. But we could take the tail of tails and cons on our new element from the last state. In which case, I'm going to get a naming thing if I import data.list. Naming collision. But I can import it qualified. So we know. And we can just have a guard on that. So we can just make sure that tail length is greater than 0. Otherwise, that would be an error. Or we leave it, because we might want an empty tail. In which case, we just don't do anything. But only if the tail length is actually 0. Which, if we get to this case here, that would imply it's less than or equal to 0, yeah. So then we just leave tail as it is. Sorry, let's post. It wants it in pre-position because I haven't set appropriate options for that. Oh, I'm already, oh, it's already in prelude. I'm already getting a shadowing area. A name shadowing thing. So don't have to do that like that. I just need a better name. Tail Elms, let's call it. Okay, that's what we'll do there. Yeah, we'll just fix up this here. Tail Elms. And then we'll take the length of tail Elms. And tail Elms prime. And we have to use that. It's tail Elms prime. Okay, so we've updated the state of it now. We just need to render the tail. So we could just do 4M in tail Elms prime do, or we could just do fill rects, which might be more efficient. So SDL is a handy one where I think we saw fill rects to render a list of although I don't know if that's what I think it is. Fill rects. No, that's not the fill rects I was thinking of. Render fill rects. Huh. Yeah, okay, let's just do it the slow way. I don't think I understand what's going on there. So 4M, tail limits due, we're just gonna take this. We get the tail element. And we got to put it here. I think that ought to do-ish, except if I could possibly put an arrow. It's got to wrap it in a P. Redundant do. Of course, it is not getting my input yet. There we go. So it's not quite the right state because we're not multiplying in the grid factor there. So it's not quite right. So let's see. Can I fmap 20 over that? What did I do? Oh, missing a bracket. Blah. Yeah. There we go. Yes. Ugh. Okay, almost. Kind of got a tail going. That original rectus sitting there, though. That's probably just a sign that our state update on the tail is not quite right. So the length of tail elements to the tail length. Yeah. Let's see how. No. So the tail of tail elements is going to take. Yeah, that's the problem there, I think. And it's kind of what I was thinking. Maybe list isn't the right thing because we're not evicting the oldest in this case. We're evicting the newest because we're always consing the last state onto the head of the list. Haskell sequence might help us, maybe. Very similar to lists, but I believe we should be able to add on the other end. They're doubly linked. So let's try that. Import data.sequence. Instead of list, we'll make it a sequence. I think it's just seek. Yeah. And then the default will be empty. So we're going to just put in seek here and import qualified data.sequence. S. We'll get the operators we need. Probably use that one. Oh, it's in containers. Okay. So we got to add the containers to our package. I thought it was in base for some reason. Okay. And then should be s dot empty. If it's a monoid, it should be also m empty, which would be easier. Okay, and then we just have to fix these here. So instead of causing onto the head, we're going to take this. We'll do tail elements with that on the right. And we'll do the same thing up here. Except we won't use a tail anymore. We'll take S dot. Not all the tails, just the first. Oh, can I drop from the left? Oh, where is it? No. I just want drop one or drop or oh. Oh, there we go. There we go. Yes. Drop. Drop 0. S dot length. Okay, let's see if that works. Impossible tail state. Okay. Should be good now. There we go. Yay, okay. Tail. So sequence saved us. Oh, I'm noticing a bug here. We actually shouldn't be able to do this in normal Snake. So that's fine. Easy to fix. Because we have our state very explicit. Sweet. Okay, so we got a snake moving around. The bug is that if we have a case here we shouldn't be handling. So less than traveling to the left, we should actually not be able to go directly to the right. We should only be able to go up and down from there. And if we are traveling upwards, we should not be able to go down. If we are traveling to the right, we should not be able to go left. And if we're traveling downwards, we should not be able to go back up. Sweet. Okay, so I can't go back up that way. Good. That's better. That feels more like Snick. Sweet. Okay. Snick. What's Snick? What about time? We got about usually about 10 minutes left on the stream, but let's see what else we can do here. What's Snake without some fruit? Let's just do one fruit at a time. That's fine. We'll do one fruit. A fruit will be a V2 Cient. And oh, you don't want the type there, of course. That's constructor. Let's put at the initial game state fruit at 2020. 2022. The blessed year of our Lord. 2022. Okay, so let's render that fruit. We'll render it before we render the snake. And we'll make it a different color too. Renderer. We'll make it red. Yeah, fill rect. Renderer. Just. And except for that, we'll do fruit. Probably don't need the $sign there, just the P fruit. Make sure that actually recompiles. There's our fruit. Although it's in pixel space, we should project that to our grid space. When we render it. So we'll fmap over that. 20. Then we'll need the $sign back maybe. Okay. There it is. That's proper. All right. And so now I should be able to collide with it, but what happens when I collide with it? Nothing, because I'm just going over it. I haven't implemented that interaction yet. But when I collide with it, we should pick a new spot for our fruit, but remove, and more importantly, grow our snake tail length by 1. Okay, so what to do with a fruit position? Well, if in the last frame the SNC's position is equal to the fruit's position, and then we should register a collision with the fruit. Which means the fruit position in this current frame is going to be updated to a new random position, and our tail length will increase. So let's do those in two separate steps. So we'll get the new fruit position first. Or the fruit position for the next state. So we'll call that fruit prime, following our kind of pattern here. So we're going to compare the fruit position from the last frame to the we don't need a full compare, actually. We just do test if fruit is equal to the v2 of the x and y from the last frame. Then something else, just fruit. Leave it unchanged. We can flip this around just by saying not equal to, and then fruit, else something. That way we can put our case down here. So we're going to need to do, we're going to need system.random. Haskell system random. Comes from the random package. We don't have a lot of time here, so I'm just going to fake it. So we'll just do v2 48, 40, and 4880, say. Okay, then when it's not yet used, so we'll do fruit equals fruit prime. Just pull this down so we can start. It's getting a little too creeping a little bit along there. Okay, so that's fruit prime. And then tail length prime. All right, so if the fruit prime is not the same as it was last frame, that means we need to increase the length of the tail by 1. And it's tail length plus 1, else just tail length. And we can put that in here. And that all compiles. Let's check our game out. Yeah. Okay. Let's compile with that fruit. Pop. Okay. Our tail length increased. I'll just make it a little bit more dramatic so you can see it on screen. We'll make the tail length increase by 10. All right, and then we collide with it. And now we got a nice long snacky snack. Right, and similarly, we'd have to implement collision with our tail. Increase the speed as time goes on. That kind of thing. Well, there you go. Sneck and Haskell, not too shabby. Not too shabby. And that's all I got for you this week, Prince. Oh, sorry, I missed you. Patterns in droves. Sorry, I was really focused on the code today. So we're using SDL2 to render here today. So it's a C library wrapping in Haskell. Pretty standard library, very cross-platform, compiles to literally everything. I think you could probably run SDL2 on a toothbrush if you really wanted to. Maybe not with Haskell, but maybe, I don't know. Who knows? Depends on how much space you got on that toothbrush. Yeah, we're using SDL2. So thanks for dropping by and chatting, by the way. Patterns in droves. If you'd like to see more, I've been developing a interactive game engine or interactive fiction engine here on this stream. I'm just taking a little break from that today just to mess around with this for funsies. We're almost done that project. And once we are, the next project I think is going to be a multiplayer game server. We're going to do a multi-user dungeon in this vein of like MUDs from the 90s. It's classic text adventures, but multiple players on a server, all interacting and fighting together. MUDs were kind of the granddaddy to modern day MMORPGs, like your EverQuests and Ultima Onlines and Final Fantasy XIV, which I'm totally into right now, World of Warcraft, and so on and so forth. The granddaddy of them all was the MMORPG, or the MUD back in the day. So we might build one in Haskell for funsies. But that'll be in a few weeks, depending on how long it takes us to finish the interactive fiction engine. So if you like that, follow, subscribe, do all that things. You'll get the notifications here on Twitch. If you're watching on YouTube, you know what to do to get updates on that as I post new videos from here once a week, usually on Tuesday evenings around 8 p.m. in the Eastern Standard Time Zone. I'm Agent Ultra. You'll find me on most of the socials under that handle, and hope you had fun. May your monads be free. May your types always check, and we'll see you next week. Peace out.